In pharmacokinetics, the speed at which an inhaled gas achieves equilibrium in the lungs is dictated by its solubility. Gases with lower blood gas partition coefficients, meaning they are less soluble in the bloodstream, saturate the blood quickly, allowing the alveolar concentration to rapidly rise to match the inspired concentration. This chart plots the blood gas partition coefficients for two common agents. Desflurane sits at 0.42. Nitrous oxide is slightly higher, at 0.46. Based on these values, the math dictates a specific outcome. Desflurane is less soluble, so it should wash into the alveoli and reach equilibrium faster than nitrous oxide. This graph shows the empirical wash-in data, revealing a mathematical contradiction. The curve for nitrous oxide actually rises steeper and achieves equilibrium faster than desflurane. How does a gas with higher blood solubility achieve a faster rate of alveolar equilibrium? Standard pharmacokinetic models calculate gas uptake by assuming that the agents are administered at comparable scales. That assumption fails because it ignores the physical, macroscopic volume of the dose being administered. Modern volatile anesthetics, like sevoflurane or desflurane, are delivered as microdoses. They typically represent between 2 and 6% of the total inspired gas mixture. Nitrous oxide is a remarkably weak anesthetic. To achieve a clinical effect, it requires a massive, macroscopic delivery. In a typical induction, nitrous oxide comprises 70. This diagram represents the Stolting and Eager alveolar model, standardizing a single breath of a high-dose mixture into exactly 100 units of volume. We fill it precisely. 80 units of nitrous oxide, 19 units of oxygen, and 1 unit of a volatile anesthetic. During the initial uptake phase, nitrous oxide diffuses rapidly across the alveolar membrane. In this model, we see 50% of that nitrous oxide, 40 units, drop into the pulmonary capillaries. As this mass of gas exits the space, the alveolus does not maintain its original size. The boundary physically shrinks down to perfectly encapsulate the remaining 60 units of total gas. We now have 40 remaining units of nitrous oxide, occupying a container that only holds 60 units total. 40 divided by 60 is 66.7%. Despite half the gas being absorbed into the blood, the fractional concentration of nitrous oxide remains artificially high. This specific mathematical anomaly is defined as the concentrating effect. The collapsing alveolar volume offsets the expected dilution, maintaining a high driving partial pressure from the lungs into the bloodstream. A common error in board exams is stopping the explanation here. The concentrating effect alone does not completely account for the rapid uptake. When the alveolar container shrinks from 100 units down to 60, it leaves a 40-unit physical void in the lungs' functional residual capacity. The lungs automatically draw in fresh gas from the conducting airways to replace this void. Crucially, this incoming gas contains the original 80% nitrous oxide mixture. This inflow effectively increases total alveolar ventilation without requiring the patient to alter their actual respiratory rate or tidal volume. The complete concentration effect is the strict mathematical sum of these two events, the concentrating effect plus inspiratory ventilation augmentation. We can apply this exact volumetric logic to the 1% volatile agent present in the original mixture, the so-called second gas. Returning to the concentrating effect, when the alveolus shrank to a total volume of 60 units, that single unit of volatile agent suddenly accounted for 1.67% of the remaining volume. Applying the ventilation augmentation logic, as fresh gas rushes in to fill the void, it drags additional volatile agent into the alveolus, increasing its total mass. The taxonomy here is specific. The concentration effect refers exclusively to nitrous oxide accelerating its own uptake. The second gas effect describes nitrous oxide accelerating the uptake of any co-administered gas. By physically manipulating lung volume, a massive dose of nitrous oxide acts as a pharmacokinetic booster, speeding up the induction of companion volatile agents. At the conclusion of a surgical procedure, the active delivery of nitrous oxide to the patient is abruptly discontinued. With the inspired concentration suddenly zero, the partial pressure gradient violently reverses. Nitrous oxide leaves the bloodstream and floods back into the alveoli. This massive influx physically displaces the oxygen inside the alveolus, driving down its concentration and causing a state of diffusion hypoxia. It simultaneously dilutes alveolar carbon dioxide. This dilutional hypocapnia suppresses the patient's respiratory drive at the exact moment they need oxygen the most. This sequence of events is formally known as the Fink effect. The Fink effect is simply the concentration effect running in reverse. The exact physics that provide a rapid induction transform into a severe clinical hazard during emergence. This differential solubility creates another specific hazard. The blood gas partition coefficient of nitrous oxide is 0.46. That is an incredible 34 times greater than the coefficient of nitrogen, which sits at 0.014. Closed physiological spaces, like an obstructed bowel loop or a pneumothorax, naturally contain trapped nitrogen. This creates a strict imbalance known as the rule of 34. For every single nitrogen molecule that slowly diffuses out into the blood, 34 nitrous oxide molecules rapidly rush in. If the surrounding tissue is compliant, like the intestinal wall, this asymmetrical transfer forces the volume to rapidly expand. If the space is non-compliant, like the middle ear, the massive influx of gas instead causes a drastic, dangerous spike in pressure. Because of these volumetric physics, nitrous oxide is strictly contraindicated in cases involving closed, air-filled spaces. The macroscopic volume required to administer nitrous oxide dictates its entire clinical profile. The sheer physical presence of the gas in the lungs drives its uniquely rapid induction and underpins its most profound physiological risks.